Thank you. Okay, so yesterday in the talk I gave a general broad outline of the program. Okay. So from today onwards I will try to provide more of the details. Okay. So today's lecture will be providing the corresponding details that I discussed for bosonic string theory. Okay, and this will be a warm up exercise, and also it will provide a lot of the information that you will be able to use in the case of superstrings and heterotic strings. So let me remind you that what are the tasks that we have to perform. Okay. The first thing is to find a suitable parametrization of the space PGN that I introduced. Okay. So PGN, let me remind you, was a fiber bundle whose base was the moduli space of genus G Riemann surfaces with n punctures, and whose fibers contain information about the possible choice of local coordinates. Okay. That is an infinite dimensional space because you have a whole function worth of variables that we can use. The next task will be the following, that if we are given some n external states, okay, which will collectively denote as phi, we want to construct these p forms omega p on PGN with the desired properties. Okay. And I will explain what are the various desired properties, but in particular we need a property that I mentioned, and this property is crucial for first of all showing that the on shell amplitudes are independent of the choice of local coordinates, but also more generally to get various identities involving off shell amplitudes. And finally, this part is somewhat independent of the second part, okay, and that is to construct doing compatible sections and also 1 pi subspaces RGN of PGN. Okay. And eventually the idea is that we will have to put 2 and 3 together to construct the 1 pi effective action or 1 pi amplitudes. So let me begin by describing a possible way to parametrize PGN, and in fact the parametrization that I will be describing is highly redundant. Okay, so you will not, for practical use you may not want to use this. In fact, there are better practical methods for parametrizing the moduli space. Okay. Nevertheless, this will be a useful way to proceed. Okay. So let us suppose that we have a genus G Riemann surface with n punctures, okay, and by a simple operation we can consider this as a union of n disks. So what are these n disks? N disks are simply some disks cut out from the Riemann surface around each puncture. Okay. So here I have denoted a genus 2 Riemann surface with 2 punctures which are these crosses, and we cut out a disk D1 around the first puncture and a disk D2 around the second puncture lying on the Riemann surface. And then we also have 2g minus 2 plus n spheres which are denoted by SIs, okay, and each of the spheres will have 3 holes. Okay. So here again I have described in this genus 2 Riemann surface how to do this cutting. So basically you draw various circles on this Riemann surface, okay, and you draw enough number of circles so that between these circles it is enclosed a 2-dimensional space which has a topology of a sphere with 2 holes, with 3 holes. You can see S1 has 3 holes, C1, C2 and C3, S2 has 3 holes, C2, C3 and C4, S3 has these 3 holes and so on.
Excuse me,
Yes.
Does your chosen parametrization also work for n equals 0?
Well, we will never consider n equal to 0 because we are considering amplitudes, right. So for us n should always be equal to 1 onwards. Okay. I mean otherwise, yeah, it can be used for n equal to 0 except that for torus, for example, right, you cannot use 0 puncture torus and the counting will go wrong. For spheres you have to have at least 3 punctures. Okay, but for us we will never consider anything other than those where n becomes 0. Okay, now I will not do this counting, but one can do a simple counting to show that when you do this division like this, okay, the number of disks is n, which is not surprising. There are n punctures and around each puncture you are cutting out a disk, but one can also show that the number of spheres is 2g minus 2 plus n, okay, and the number of circles that you will get is 3g minus 3 plus 2n. Okay. So for genus 2 and n equal to 2, which is the case that is relevant here, okay, this number is 4, okay, we indeed have 4 spheres, and this number is 7, Okay, we have 7 circles as you can see from here. Okay. So, given this division, we will now introduce complex coordinate system on each component. Okay. So, we will denote by WA the complex coordinates on each of these disks dA, and we will choose the convention that the puncture, the ath puncture will be at WA equal to 0. Similarly, on each of the spheres, we will introduce a complex coordinate Zi. Now, if Si and ds share a common boundary, okay, like for example S1 and D1 here shares a common boundary which is C1, okay, then on the boundary we have a relationship that tells us give Zi as a function of Wa or vice versa. Okay. So, there will be a relationship of the form Zi equal to Fia of Wa. Similarly, if Si and Sj share a common boundary, like for example S1 and S2 here share this common boundary C2, then on the boundary we have a functional relationship that relates Zi and Zj, okay, which I will denote by these functions Fij. Okay. Are there any questions? Okay. And so now the idea is that these transition functions, okay, Fia and Fij, okay, these contain complete information on the Riemann surface and the choice of local coordinates. Okay. It is clear, right? Once you specify these transition functions completely, then the Riemann surface is completely fixed. There is nothing else to specify. Okay. And the choice of local coordinates is also fixed because it tells us how the local coordinates W are given in terms of some coordinates that we have chosen on the Riemann surface. So, you can use these transition functions as coordinates of PGN, because once these transition functions are given, then PGN is completely fixed. But we should keep in mind that this is a highly redundant parametrization. Okay. Lot of this information that is in the transition function is quite trivial. Okay. For example, imagine that we make an arbitrary reparametrization of one of the z's. Okay. A reparametrization that makes that is well defined on a sphere with 3 disks removed. Okay. Each of the SI is a sphere with 3 disks removed. So, let us imagine that we make an arbitrary reparametrization of the ZI's, okay, which is well defined on that space spheres with 3 disks removed. Okay. Clearly, they give the same point in PGN, okay, because they are not changing the choice of local coordinates. Local coordinates are encoded in the W's, okay, and neither are they changing the Riemann surface. It is just a different way of coordinatizing the same Riemann surface. Okay. Nevertheless, these changes will change our transition functions, right? It will change both the small f and capital F's. So, those changes are in some sense trivial deformations of PGN. Okay. They are not really parameters of PGN, that is redundant information. Now, in general, if we reparameterize W's, okay, then that is not trivial in PGN. Okay. If you redefine your coordinates WA, okay, it keeps the same Riemann surface. Okay. It is not changing the moduli of the Riemann surface because it is still a coordinate transformation. But changing WA changes the choice of local coordinates, okay, because WA's will be chosen to be the local coordinates around the punctures, okay, and PGN involves information about the local coordinates. So, changing a reparametrization of W will typically move you along the fiber. Okay. However, we will impose one restriction, okay, or one identification, namely that if we change WA by an overall phase for some constant alpha, then these reparameterizations are defined to give the same point in PGN. Okay. In other words, PGN will contain information on the local coordinates, but only up to phases. Okay. This is necessary because without this additional identification, okay, you do not have sections, okay, which is over which you want to integrate. Okay. But as we will see that this will not matter eventually in the final result. Okay. But this is an important point to keep in mind. Yes. Yes.
Why shouldn't you consider alpha to be a rotation matrix in the general case? I mean, the condition for the point is that it's at omega 0 or
yes.
W 0.
Yes.
So you could you have a set of coordinates omega for each point.
Yes.
So you could rotate them and still have.
Yes, yes, that's right. So each W can be rotated by an independent parameter.
So it's not a pure phase, but a rotation matrix, say.
Well, I mean, you can. It's a diagonal matrix, right? I mean, the number of parameters that we are using to identify is precisely the number of punctures, because around each puncture you can introduce rotate WA independently, right? So you can write it as a matrix, okay, a diagonal matrix where each WA, you are not mixing the W1 with W2,
Yeah, yeah.
right? Because they are of course different coordinates.
Okay,
so each WA is getting rotated by a phase. Okay, any other questions? Okay. So next thing we want to understand is the tangent vectors of this space. Okay. The reason that you want to understand the structure of tangent vectors is because we are eventually interested in defining forms. Okay. And the way we will define forms is by specifying how they are contracted with the tangent vectors. Okay. Because a P form can be contracted with P tangent vectors to yield a number. Okay. And we will be providing you the expression for that number. Okay, so you want to understand how to label the tangent vectors. So tangent vectors of PGN will correspond to infinitesimal changes in these functions, right? Because what the tangent vectors correspond to is small motion, infinitesimal motion in this space in PGN. Okay. So for example, let us suppose that we change Fia by a small value, small function delta Fia. Then that means that the original relation Zi equal to Fia will go over to a new relation which is Zi equal to Fia minus delta Fia. Okay. So these delta Fias will label possible deformations of PGN, okay, and will label a tangent vector of PGN. Okay. Similarly, you can do a same thing with this should be capital Fij. We can do it with the capital Fij's. Now, let us focus on this case. Okay. Suppose you have deformed the functional relationship by this. Okay. Now, given this, we can introduce an infinitesimal vector field on the Riemann surface and on the common boundary of Si and dA, okay, and this is the way you define the vector field. Okay. So, the vector field defined as a function of the Zi, okay, is the same delta Fia, but all we have done is that instead of thinking of this as a function of Wa, I have re-expressed Wa as a function of the Zi's. Okay. So this gives you a vector field on the boundary between Si and dA expressed as a function of Zi. Okay. When I say that this is a vector field on the boundary, in fact this is a vector field in some small band around the boundary. Okay. It's defined in a small band around the boundary. There is no requirement that this vector field should be globally defined. Okay. Away from this small band, it can become singular. Okay, it can allow arbitrary singularities from this band. Okay. So this kind of vector fields label infinitesimal tangent vectors of PGN. Okay. And similarly, you can play a similar game around each such overlap circle. Okay. For each circle, you can consider a vector field around that circle, okay, and that labels a possible tangent vector of PGN. Okay. But again, lot of these tangent vectors are in fact 0. Okay, because they are induced by reparametrization of coordinates, okay, and they do not move you in PGN at all. Okay, and I have described this here. Okay. So let us suppose that we carry out a small reparametrization of Zk of one of the coordinates on Sk. Okay. Now clearly this does not induce any change in the Riemann surface or the local coordinates at the punctures. Okay, so it keeps you at the same point in PGN. Okay. So it should give a 0 tangent vector of PGN. Okay. Nevertheless, okay, when we translate it to this vector field notation, okay, when you compute this delta Fia or delta Fij, okay, they are non-zero in general, right? Because if you change one of the Zk's, keeping the other Zi's fixed, the overlap function will change. Okay, so you will get a different functions. Okay. So, you will get a collection of vector fields associated with a reparametrization of Z, okay, and those have to be declared as 0 tangent vectors, okay, even though they are non-zero as vector fields. Okay, so, this is what I have said, that these deformations must be declared as 0 tangent vectors of PGN.
Do yes. These reparametrizations leave the punctures invariant?
Yes, if you reparameterize the zi's, right, the punctures are WA equal to 0, so you are not doing anything to the punctures, right. So, clearly they leave the punctures invariant. They are not only leaving the punctures invariant, they are not even changing the local coordinates, because the local coordinates are encoded in W, right. So, if you reparameterize W's, then they in general change the local coordinates, so they move you along the fiber. Okay. Reparametering Z does not do anything. So, this basically finishes our brief introduction to the how to parameterize PGN and its tangent space. Okay. As I have already said, that this is not a practical way of parameterizing PGN, okay, because this is highly redundant. Okay. There are better parameterizations of PGN, but we will just keep this in mind because we will be defining various things in terms of this parameterization. Okay. Are there any questions? So, now then let me turn to the next topic, okay, which is how to construct these P forms omega P of phi on PGN. Okay. So, here is a quick summary of bosonic string theory, okay, and some of the notations. So, bosonic string theory is based on a matter conformal field theory of C equal to 26 and a ghost conformal field theory of C equal to minus 26. Okay. And in particular, this theory contains ghost fields B, C, B bar, C bar. These are holomorphic and these are anti-holomorphic ghost fields. Now, we will denote by H the Hilbert space of the combined CFT, okay, but we will not allow a most general state in this Hilbert space. Okay. We will allow for Hilbert space, allow for states in the Hilbert space which are annihilated by these combinations of B's and L's. Okay. So, B0 minus B0 bar is these are the 0 modes of the B ghost, okay, and L0 minus L0 bar, these L0 and L0 bar are the 0 modes of the Virasoro generators. Okay. This is necessary. So, when we talk about off shell string states, okay, we will relax constraint of BRST invariance, constraint that they are primary operators, that they have dimension 0, etc. Okay. However, we will keep these constraints that they must be annihilated by L0 minus L0 bar and also by B0 minus B0 bar. Okay. As it turns out, this is sufficient for our purpose. Okay. We do not need more general off shell configurations than this one. Okay. The necessity for this, okay, comes from this fact that we cannot choose local coordinates, okay, including phases. Okay. The local coordinates are to be chosen up to phases, okay, and that so the point is you have to make sure then that phase rotation, okay, is a trivial operation, right, because nothing should be sensitive to the phases of the of the local coordinates, and that in particular is guaranteed by these conditions over here. Okay, maybe I will say a few more things about it later. Okay. So, given a Hilbert space defined this way, I will denote by this the n-fold tensor product of H. Okay. This is a convenient notation because if you are talking about n external string states, okay, then they give an element of this n-fold tensor product of H. Okay. And finally, this notation will denote the standard BPZ inner product between the conformal field theory states. Any?
Both of B0 and L0 are the Virasoro operators.
No, L0 are the Virasoro generators, B0 is the 0 mode of the ghost field B. These are the modes of B. These are ghost fields, right?
Yes, there are different central charges and B0 related to parameter, yes.
Yeah, B0 is related to basically B0 is the 0 mode of B. B has a mode expansion, right? Sum over n B n z to the n minus 2, and so. No, this is the standard mode expansion of conformal fields, right? If you have holomorphic fields, right, it can do a mode expansion, and this is a 0 mode of that holomorphic field. Okay. So now I will have to introduce some more notations. So let us consider a point in PGN. Okay. Now what do you mean by a point in PGN? Okay. A point in PGN corresponds to a Riemann surface S of genus G and n punctures. Okay. But given this point in PGN, you also have a specific choice of local coordinates at each puncture. Okay. Because a point in PGN means that you have fixed the location on the base as well as on the fiber. Now, to this point, okay, we can associate a particular state which we will call the surface state, okay, in the n-fold tensor product of H by this following procedure. Okay. The way we will specify this state H is by specifying its BPZ inner product with an arbitrary state in this tensor product. Okay. Since the inner product is non-degenerate, once you specify the inner product of a state with an arbitrary state, okay, then the state is fixed. Okay. So, I will specify the inner product of S with an arbitrary state phi in this tensor product, okay. And here is the definition. Okay. The inner product is by definition the correlation function of n vertex operators that are encoded in phi. Phi, let us recall that this is the tensor product of n states. So, there are n vertex operators that are encoded by phi. Okay. So, you compute the correlation function of these n vertex operators on the Riemann surface S, okay, the same Riemann surface S, but they have to be inserted with the chosen local coordinate system, right, because a point in PGN not only specifies the Riemann surface S, but also the choice of local coordinates. Okay. And this correlation function has to be calculated with those specific chosen local coordinate system in which we insert a vertex operator. Okay. So, this gives a completely well defined number, okay, and that number, okay, is declared to be the inner product between the state S and the state phi. Okay. You can do this for every state phi, and this in turn determines the state S completely. Okay. So, this is the definition of a surface state. Okay. To every point in PGN, you can associate a state in the n-fold tensor product of H. Okay. Are there any questions? Is this clear? Okay. Now, given this, okay, we are ready to start defining the omegas. Okay. So, omega 0, okay, which is the simplest, okay, as a function of phi is simply the same, the inner product of S with phi. That means, it is the correlation function that we described here with some specific normalization factor which is here. Okay. This normalization factor is necessary for various factorization properties that we will use for omega 0. So, now we have to define the omega p's for general p. Okay. Let us recall that omega p of phi is a p form on PGN. Okay. Now, what is a p form? Okay. One way to specify a p form, okay, in differential geometry, suppose you want to specify a p form, one way to do this is to choose a coordinate system, and then a p form is specified by its components, okay, which means that given a set of p tangent vectors, okay, the contraction of the p form with those tangent vectors is a number, okay, and as long as you specify the number for every choice of tangent vectors, then the p form is completely specified. Okay. It is a component of the p form along every tangent vector. Okay. So, what we need to do then to specify a p form omega p is the following, that given p tangent vectors of PGN, we have to specify how to contract omega p with these tangent vectors. Okay. So, the contraction of omega p with these tangent vectors is a number. So, if we specify this number for every choice of p tangent vectors of PGN, then you have defined our omega p. Is this clear? Okay. So, I will now describe what this number is. Okay. So, to describe these numbers, you have to recall that tangent vectors of PGN can be labeled by vector fields Vi on S around some circles. Okay. That is how we label the tangent vectors. Okay. change the transition functions. Each transition function can be changed by an infinitesimal amount, and that will induce a vector field on the overlap circle. Okay. So, one way to label the tangent vectors of PGN are basically giving vector fields which are well defined along in a small band around each circle, around these circles. Okay. So, given such a vector field Vi on the Riemann surface, okay, we will define this object capital B of Vi as the integral, contour integral along these circles of this combination. Okay, Bz times Viz and B bar Z bar times Vi bar Z bar, where B and B bar are the B ghosts and the B bar ghosts as we introduced earlier.
Just a question. What about the conservation of the ghost number?
Yes, so the conservation of the ghost number will be automatic. Okay, will be automatic in the sense that it will. So let me define this omega p first, and then I'll talk about the conservation of the ghost number. Okay, so omega p phi contract with V1 to Vn is given by this object over here. Okay, I have already defined the surface state S. Okay, now instead of taking the matrix element of inner product of S with phi, we insert these operators B V1 up to B Vp, and then take the inner product with phi. Okay, now let us come to the conservation of ghost number. Okay. This is a genus G surface. Okay. So, total ghost number, total B ghost number, ghost charge has to be 6G minus 6. Okay. So, what this means is that this will vanish, okay, unless the total B ghost charge of these, which is P in number, plus the B ghost charge of phi adds up to 6G minus 6. Okay. So, conservation of ghost number is built in into the correlation function. Okay. Unless the ghost number is conserved, the result vanishes. Okay. Omega p does not have components along those tangent vectors. Okay. Is this definition clear? Okay. These ones? Well, this one, no, this is not radial ordering, this is just contour integral. Right? It is a single operator, there is a product over here. V's are just numbers. Right? So, there is no radial ordering here. This is B of Z, there is a single operator here, okay, multiplied by a function and integrated along this contour. Okay, and here the only thing that matters is that these things all anticommute with each other. Right? So, the ordering, if you change the ordering, you pick up a sign, okay, which is of course not surprising because omega p is a p form, right. So, if you change the ordering of the tangent vectors, you will pick up a sign.
Can we think of these VIs as Beltrami differentials, or are they holomorphic? Right?
Yeah, BIs are these are like Beltrami differentials, okay, written in a specific parametrization.
So is the integrand holomorphic?
Is
the integrand meromorphic?
Yes, if Vi of Z, the way I have defined, okay, this is meromorphic. Yes, so this is defined. This is analytic around that band, right, but it does not have to be defined elsewhere.
Just to understand, B of Vi acts on the H of, on the Hilbert space associated with the ith external state.
No. Okay. The point is, the way to interpret this, this you can rethink, okay, as a correlation function, okay, on the Riemann surface. Okay. So, without these B's, okay, this correlation function would have been just the correlation function of the Riemann surface with these states inserted at the punctures. Okay. Now, all you are saying that you calculate the correlation function with this additional B's inserted on the Riemann surface, right. So, you do not have to have the Hilbert space interpretation. Okay, this is perhaps this is a formal way of writing it. Okay, you just interpret this as a correlation function on the Riemann surface with those external vortex operators corresponding to phi inserted at the punctures, okay, and the integrals of B's, okay, inserted on the Riemann surface. That is a perfectly well defined object, right. So, that is the interpretation of what this means. Okay. Now, of course, one has to make sure that this definition is consistent. Okay. What do you mean by this definition is consistent? Okay. First of all, there are many tangent vectors which are 0 as tangent vectors of PGN, okay, but they correspond to non-trivial vector fields, right. The vector field looks like you define introduce non-zero vector fields which are induced by reparametrization of the z's, okay, but they we know that those are 0 as tangent vectors. Okay. You have to make sure that when omega p is contracted with such tangent vectors, you get the answer 0. Okay. So this is something we can explicitly check, okay, that if any of these vector fields are induced by reparametrization of one or more of the zi's, then omega p automatically vanishes. Okay, you can show it by basically deforming the contour integral of the b's. The second identity, which is what we have been aiming for, is this one. Again, this is something you can show explicitly using the expression that I gave before, in the basically using techniques of conformal field theory, okay, on Riemann surface. You don't really need anything more than just standard manipulation of conformal field theory to prove this once omega p has been defined. So now let us recall that what we are going to do omega, what we are going to use omega p for. Okay. One of the uses of this omega p is that if we have chosen a specific section of PGN, okay, that we declare as a section over which we will do the integral, then the off shell amplitude will be given by integral of omega 6g minus 6 plus 2n of phi on this section. So the first thing we should check, okay, is that if the external states are on shell, if they are BRST invariant, okay, then we better get back the usual expression for on shell amplitudes, right, which you know are given as integrals over the moduli spaces of Riemann surfaces. Okay. This is something again one can show explicitly that given the expression for the omega that we have, okay, if these external states are all on shell states, BRST invariant dimension 0 vortex operator, then you can explicitly check that this integral, okay, gives back the usual on shell amplitudes in string theory that we express as integrals over the moduli spaces of Riemann surfaces. Okay. Are there any questions? Yes.
So is this true by construction or?
Yes, it is essentially true by construction. The way you have defined the omega p, right, it is designed so that this happens. Okay. But it also has the additional feature that even for off shell states, okay, it obeys this identity that we gave here. Okay. For on shell states, okay, we could omit this statement. Okay. We said that in the definition of S, we have to insert these vortex operators with the chosen local coordinate system. Okay. This is we could avoid. For on shell states, there are the dimension 0 vortex operators, so the result does not depend on what local coordinate system you use. Okay. So this is the additional input that allows us to derive this identity of shell. Okay. So now I turn to the final task, okay, which is to choose gluing compatible sections of PGN, okay, which we denoted by SGN earlier, and once we have this gluing compatible section, that will also tell us how to construct these 1pi regions which we called RGN. Okay. So I will try to describe this procedure. Okay. So we begin with the simplest possibilities, which is 3 punctured sphere and 1 punctured torus. So 3 punctured sphere has a 0 dimensional moduli space, okay, and a 1 punctured sphere has 1 punctured torus has 2 dimensional moduli space. Okay. Basically the tau parameter that labels a torus. The location of the puncture is not a parameter because there is translation invariance on the torus which allows you to fix the puncture at any point that you like. Okay. So the idea is that for these, okay, we can choose the local coordinates of the punctures arbitrarily in any way you like, but it is not completely in any way you like. Okay. You should choose them so that they are consistent with symmetries. Okay. So what are the symmetries? For example, for the 3 punctured sphere, okay, we have exchange of punctures. So you can exchange the punctures, okay, and you should choose the local coordinates so that under the exchange of punctures the local coordinates also get exchanged. Okay. This is a convenient choice, I have more to say about this maybe at the end, okay, how we go about doing this. Similarly, for one punctured torus, okay, we have modular transformation. Okay, so one punctured torus, the fundamental domain, okay, is this. Okay. So, for example, we know that these two lines are identified. So, you better make sure that the local coordinate that you have chosen when tau is this is the same as the local coordinate that you have chosen when tau is this. Okay. Similarly, there is an identification of this with this. So, the local coordinate at this value of tau should agree with the local coordinate at this value of tau and so on. Okay. So, this is what we mean by it should be consistent with symmetries. Okay. But other than that, we do not impose any other condition, you choose them any way you like. Okay. So, choosing specific local coordinate system means that we have chosen sections of P03 and P11. Okay. Now, P03 of course MGN is just a point. Okay. So, we only have the fiber direction. So, a choice of local coordinate system basically means that we have chosen a point on the fiber. This is for P03. For P11, MGN is 2 dimensional, so we still have a non-trivial section, okay. And a choice of local coordinate system means that we have chosen the local coordinates for every value of tau in the fundamental domain. Now, for these P03 and P11, we declare these sections, okay, all the Riemann surfaces that are contained in these to be 1pi subspaces of P03 and P11, okay, which means that you declare that R03, the 1pi region, is the same as the full region. Okay. Here of course, there is not much you can do, it is just a point after all, right. So, what can you do? You have to declare S03 as R03, but here also, okay, you declare that R11 as the whole of S11. Okay. Now, it is not very surprising from either the field theory viewpoint or the Riemann surface viewpoint, okay, because if you just think of it a little carefully, you can see that if we have a 3-point function, okay, which is tree level 3-point function, right, it is always one particle irreducible. There is no way you can get a tree level 3-point function, okay, from one particle reducible graphs. Okay. Similarly, a one loop 1-point function is always one particle irreducible, right. There is no way to draw a graph in any field theory where a one loop 1-point function contains one particle reducible contribution. Okay. So, that is the reason why for these we declare that these are the same. Okay. This is also true for Riemann. If you think in Riemann surface language, there is no way that we can take a 3-puncture sphere and think of this as a plumbing fixture of some smaller components, okay, or a 1-puncture torus. You cannot think of this as being obtained by plumbing fixture of any smaller components. Okay. So, now we take 2 of these 3-punctured spheres, okay, and we can glue them using plumbing fixture. Okay. So, take 2 of these 3-punctured spheres, glue them using plumbing fixture, which means that you identify ZW equal to the minus S plus I theta. Let S run from 0 to infinity, theta run from 0 to 2 pi. Okay. Now, this we in fact worked out this a specific example yesterday by choosing local coordinate system. Okay. But it is clear from this general description that as you let S run from 0 to infinity and theta run from 0 to 2 pi, this gives you some 2-dimensional 2-parameter family of 4-punctured spheres, right. This is clearly a sphere with 4 punctures, and as you let S and theta run over their complete range, this gives you certain 2-parameter family of 4-punctured spheres. Okay. Now, you can also recall that 4-punctured sphere has 2-dimensional moduli space. Okay. So, basically what we are getting by this procedure is a subspace, a 2-dimensional subspace of this 2-dimensional moduli space of 4-punctured spheres. Okay. You declare those to be 1 particle reducible 4-punctured spheres, and we choose the local coordinates at the remaining punctures to be the ones that is induced from the 3-punctured spheres. and then we have to repeat this for inequivalent permutations of the 4 punctures, because the punctures are distinguishable, right, because they can have different states inserted at these punctures, right. So, if we call this 1, 2, 3, 4, okay, you also have contributions as 1, 3, 2, 4 or 1, 4, 2, 3. We can think of this as sum over ST and U channel diagrams. Okay. All of these are declared to be one particle reducible, okay, and the local coordinates have to be chosen according to what is induced from this gluing procedure. Okay, is this clear? So, typically the 4 punctured spheres that you obtain this way will cover part of the full moduli space of 4 punctured spheres. Okay. We declare these to be one particle reducible 4 punctured spheres, and on the rest of the 4 punctured spheres we choose local coordinates arbitrarily, but of course you have to be consistent with the symmetries, okay, and make sure that it is continuous, and declare them to be 1 pi 4 punctured spheres. Okay. So, in diagrams what we are seeing is the following. Okay. So, typically the situation is that if we consider P, here we are considering P04, okay, and this is M04. When you put the S, T and U channel diagrams contributions together, okay, what you get is some part of the moduli space of 4 punctured spheres, okay, and the idea is that, so these are all one particle reducible contributions, and you have to fill the gap. Okay, you can do anything that you like here, okay, choose the sections arbitrarily, but you have to make sure that it is continuous, that you start from this end and end here, and this is the part, this is the subspace of P04 that you declare as R04, okay, one particle irreducible contribution. Okay. The choice is quite arbitrary because you can make this go up and down, okay, which basically means that you can choose the local coordinates in the in between here in this interior region in arbitrary way. Okay. So, this is how you define, okay, the 1 pi region subregions of P04. Is this clear? Similarly, we can glue 3 punctured spheres with 1 punctured tori. Okay. So, this way we will get a set of 2 punctured tori. Here is a diagram, this is a 3 punctured sphere, this is 1 punctured torus. We are gluing 1 puncture from the sphere with the puncture from the torus, okay, and this clearly topologically is a torus with 2 punctures, right, because this whole thing, it's basically you take a torus and blow up a certain region into a sphere and insert 2 punctures, right, it is still a torus with 2 punctures. Dotted line is R04. This is what you have to supply, which is missing, right, from the 1 PR contribution. Pardon?
Maybe I'm not too. R is a radius for this.
No. This is the 1 PI region. We introduce the notion of RGN. Okay, when we are not. No, this is not amplitude. This is a region of the moduli space. This is what we call R04. This is a region of the model of PG04. Okay, a region of this fiber bundle, which will define for us the 1 PI region. Yes, so it provides a certain region of the moduli space as well as the choice of local coordinates in that for every point on the moduli space. Okay. Okay, so now let us do a dimension counting. What is the dimension of this space? Okay. So you see that a 1 punctured torus already had 2 real dimensions, right, or one complex dimension. Okay. We get 2 more parameters from the S and theta. So this together gives a 4-dimensional subspace, 4-dimensional subspace of the moduli space of 2 punctured torus. Okay. And indeed the moduli space of 2 punctured torus is 4-dimensional, okay, because you have to specify the moduli of the torus, which is one complex parameter, and the location of the one of the punctures, which is one complex parameter. So there are 4 real dimensions. Okay. So this gives you some 4-dimensional subspace of the full 4-dimensional moduli space. Okay. So you declare all of these to be 1 PR and choose the local coordinates to be the ones induced from the constituents. Okay. So this will typically cover part of the moduli space of 2 punctured tori. Okay. So we will declare the rest of the 2 punctured tori to be 1 pi and choose the local coordinates on them arbitrarily, maintaining symmetries and continuity. Okay, exactly as we did here. Okay. Now I should also say that while this picture is sufficiently generic, you can always choose local coordinates so that you have this picture. Okay. If you don't, you can in principle try to choose local coordinates in such a way that the picture is slightly different. Okay. It may so happen, for example, that instead of covering a subspace of the moduli space, you cover part of it twice. Okay. That this part is covered both by the S channel diagram and T channel diagram, right. It could happen if you are not careful in choosing the original local coordinates. Okay. But it really makes no difference, okay, because these are oriented integrals. So all you have to do is that you have to fill the gap. Okay. So you define your R04 to be this one, this part. Okay. Basically you have to make sure that you get a continuous section at the end, okay, by providing the R04 to fill the gap. Okay. And the same thing can be done for other cases. Okay. Are there any questions? Okay. So basically we now repeat this. Okay. Now that you have gotten the definition of 1 pi subspace of R 1 pi subspace R04 and R11, okay, we take those 1 pi surfaces and start gluing them, okay, and producing higher genus Riemann surfaces with higher number of punctures, okay, in all possible ways. Okay. And anything that you can produce by plumbing fixture of 1 pi objects, you declare as 1 PR. Okay, you remove them from the moduli space, and then you have to make sure that whatever gap is left over like this, okay, you have to fill, okay, and you fill those by drawing some arbitrary regions, okay, between to interpolate, and those regions you declare as your 1 pi regions for the corresponding Riemann surface. Okay. So at the end of it, okay, what we arrive at is typically that for every PGN, okay, you can identify some RGN which will declare as 1 pi subspaces, okay, and the full section is obtained by basically gluing these RGNs with each other in all possible ways. Once you have done this, okay, we can define the full off shell 1 pi amplitude as the integral of omega over RGN. Okay. And if you want the full, this is off shell 1 pi amplitude, if you want the full amplitudes, you have to do the same integral, but now over the whole of SGN. Okay. This is the only difference between the off shell amplitudes and 1 pi amplitudes. Okay. Is this point clear? Yes.
Is it possible that by very clever choices of local coordinates you could eliminate the need for some of the
yeah, it's not obvious that you cannot do it, but there are theorems which says that you cannot do it, that it's impossible to find local coordinates by which you can eliminate the RGNs altogether. Yeah, I mean that would have been nice, because then we could work with a simpler theory, simpler 1 pi effective theory, right, if you could eliminate many of the RGNs. Yes.
Do you require the external states to have a ghost number 2, or could it be anything?
Well, at this stage we are not restricting the ghost numbers, except that the ghost charge conservation will make some of the omegas to be 0. Okay. But eventually when we actually define the 1 pi action, we will be restricting the ghost number 2 external states. Okay. But the reason that we are defining this in general is because we will also be studying gauge invariances, right, and the gauge transformation parameters will involve ghost number 1 states, for example, right. So, that is why at this stage you do not want to fix the ghost numbers. Any other questions? Okay. So, I just want to end by mentioning one subtle point, okay, which is a useful trick to keep in mind. Okay. And the point is the following, that we have said that we have to choose the local coordinates to be consistent with all the symmetries. Okay. That, for example, if we take a 3-punctured sphere, okay, and we make an SL2C transformation that exchanges the punctures. Okay. Typically, that SL2C transformation will change the local coordinates. Okay. But you have to make sure that local coordinates are chosen in such a way that they are exchanged appropriately under this SL2C transformation. Okay. This is possible, but it is a reasonably strong constraint. And suppose for some reason we do not want to impose, we want to choose the local coordinates differently, okay, without explicitly imposing this symmetry. Okay. This is not important here, but this is actually important in fermionic string theory. Okay. So, that is why I am mentioning it here. Okay. So, even if it is possible, it may not be convenient to make a single choice of local coordinates that is compatible with all the symmetries. Okay. So, the question is it possible to do something which allows us to incorporate this situation, okay, whereby making a single choice of local coordinates you may not be able to have all the symmetries built in. Okay. And it turns out that it is possible to do this, and that is the following. Okay. So, the way we get around it is that we can in principle allow these sections SGN, okay, to be weighted average of several subspaces, okay, or several sections. We said that we choose a given section and integrate the omega over this section to get the off shell amplitude, but that is not necessary. Okay. We can take them to weighted average of several subspaces, which means that formally we can take SGN to be of this form, where each of the SIGNs are sections and AI satisfy the sum over AI is equal to 1. Now, this is of course formal, okay, but even though this is formal, okay, this is perfectly well defined, okay, because after all this is what we will use this for, this SGN for, okay, to integrate forms on these subspaces. Okay. So, the definition of integrating this omega 6g minus 6 plus 2n over SGN, okay, is simply that we integrate omega 6g minus 6 plus 2n over each of the SIGNs and take a weighted average with the same coefficients AI which appear here. Okay. That is the meaning of what we mean by integrating over a subspace like this. Okay. So, this allows for a more general set of subspaces, and now for example, okay, we can choose these SIGNs in such a way that under a symmetry transformation these SIGNs get permuted. Okay. So, a single SIGN may not obey those symmetry requirements, okay, but by including sufficient number of SIGNs we can make sure that you have the symmetry of this SGN. And we can extend the notion of gluing compatibility and construction of one pair subspaces to this case as well. Okay. It is a little technical, but it is definitely possible. Okay. So, in many cases, at least in fermionic string theory, okay, we will have to make use of more general subspaces SGN of this kind, okay, nevertheless which has to obey the same constraints of gluing compatibility and existence of one pair subspaces. Okay, I think I will stop here. So, next time we will start with the fermionic strings.
Please. So, here,
yeah.
To what extent do you need a more detailed, I mean, what properties of these decompositions do you need to make this amplitude more than a formal object?
More than well, this is of course not a formal object, right? This is a perfectly well defined object, right?
Well, it's well defined to the extent that you can actually prove certain properties of SGN.
Yes, so you, at the
sorry,
level
the
of
one-
SGN, it's a formal
hadn't-
property.
No, I had in mind the 1 pi action, I mean amplitude.
Yes.
So even you've shown us M04 and M12, which are the
Yes.
very easy cases. But even for M05, could you build the decomposition and as pictorial as this one, for instance?
Yes, you can do it because what you have to do for M05 is that you to build M05 you have two classes of 1 pi amplitudes at your disposal. One is this one, okay, 3 punctured sphere, okay, which is all 1 pi, and 1 pi 4 punctured spheres. Okay. Now you draw all possible graphs, okay, which you can of course translate to Riemann surfaces with plumbing fixture, okay, involving these graphs. Those are all declared as 1 pi region of M05. Whatever is not covered, okay, you declare as the 1 pi region. Right? So the algorithm is completely general. Right? You basically build the 1 pi graphs first, 1 pi contributions first by plumbing fixture of all the 1 pi contributions and see what is left.
But I mean, can you get around the double counting issues that easily? Is that
no? You don't have to. Yeah, you can get around. So one, I mean, I'll describe one way to get around double counting, but I'm saying that you don't have to get around double counting because you can do this. Right? This is double counting, right? You are counting this twice, okay? But you can, all you have to do is to make sure that there is an interpolating region that connects smoothly, okay?
How can you make that sure?
How do you make that sure? Meaning, given these two sections, right? This is a one-dimensional graph, of course. I mean, you can generalize to higher dimension, but that you can easily check that it can be done. Okay? You just have to make sure that it has no boundary, right? Whenever it looks like there is a boundary, you keep extending it and join it to the other part. Okay? But one way to avoid the double counting, okay, is that the original choice of local coordinates that you make on the 3 punctured sphere, okay, you take these W's to be Z over, so suppose Z is some global coordinate system on the sphere, okay, you scale the W's by a sufficiently large number, by sufficiently small number, so lambda should be, okay, let me write it as W equal to lambda Z, so lambda should be sufficiently large. Okay. So this basically means that if we consider the mod W equal to 1, okay, this is the circle, this is actually a very small region in the Z space. Okay. If you choose the local coordinates this way for sufficiently large lambda for each case, okay, then you can show that you can avoid the double counting. Okay. So it is certainly possible to choose the local coordinates to avoid double counting, okay, but it is not necessary. Even if you don't do this, okay, you have overlaps like this, but you can always interpolate between the ends.
Then let's thank the speaker again. And